Okay, so today is my last lecture, and when I asked to teach this course about coding theory, I thought, okay, nice, I can explain the basic about coding theory, but you know, I also like to explain a little bit about the things that I do. So the lecture today, I took a little bit the freedom to, I'm going to talk about coding theory, but more related with the kind of things that I do, okay? So basically today, I wanted to explain like two different things to you. One, I wanted to talk about algebraic codes, because, algebraic codes are made with curves. I'm going to give the definition, okay? And I work with curves, so this is why I wanted to explain this kind of code. But why are those codes important? Because again, somehow I explain, we were discussing this thing during the last week, right? When you have a code, you have the question about, if you are looking for a good code, of course you want the good properties about having like a long big minimum distance, fixing the dimension and the length, but also it's important the way that you describe the code, and the coding and the decoding, the encoding and the decoding. Okay, so those algebraic geometry codes, they have those good properties, okay? But then I realized, maybe this is very technical, so if I really want to give you the definition and study some properties of these algebraic codes, algebraic geometry codes, actually you need to know a little bit about curves. And I'm not very sure that all of you, because this school is not about curves, right? So it's perfectly fine if you don't know about it, you don't have to. But okay, so I decided, okay, I'm just going to give the definition, I'm going to state the properties, and then in the notes you have the proof about the parameters of the code that I'm going to describe that they are true. But I'm not going to do it in the whiteboard because I know you don't need to know about all this thing about curves, okay? So this is going to be the first thing I'm going to explain today. And then the other thing is the thing that I've been promising during all the week, so the crypto applications. So I'm going to show you a crypto system that is based on codes. And then I'm going to discuss a little bit about the advantages and disadvantages of this crypto system based on codes with respect to other ones, okay? So I hope it's not going to be so hard today, the lecture. You tell me. Okay, so let's start. So algebraic geometry GOPA code. So we start with X and absolutely irreducible and non-singular curve over FQ. So even I'm not sure that you know the definition of a curve. So in case you don't know, a curve is just something given by equation and that the dimension is the right one. So if you want an example of curves, you have, for instance, elliptic curves. An elliptic curve is a curve, okay? Or something given by an equation, x to the 4 plus y to the 4 plus z to the 4 equal to 0. This is a curve, okay? This, for instance, the one that I told you is the one that is called the Fermat curve, because it's like the Fermat equation, okay? So you just take a curve, define over a finite field. Now you take some points, P1 to Pn, in your curve. This n, pay attention, is going to be the length of the code, okay? Now you take another set of points, Q1 to Qm, in the curve. Those ones, you want all of them to be different. You will see why, okay? And those ones, you want all of them to be, they may be equal between them, but they have to be different from the PI, okay? So, QG different from PI. So now I'm going to define the algebraic geometry code as follows. C, D, G, so D is the set of those points, and G is the set of those points. Here, for the ones that know the terminology, actually D is a divisor. I don't know if you're familiar with this thing. So, I mean, it's more than a set, there is an instructor. But I mean, for the ones that you don't know, this is just a set of points, so don't worry. So I'm going to define my code. So I mean, somehow, because I'm going to discuss later the parameters of the code, so you're going to see that this is a good code. I'm more interested about that you see how it is constructed than really about the specific things. I mean, it's just for you to know that given a curve and a set of points, you can construct a code, okay? So what I do is that I'm going to evaluate at the points that I fixed, the first one, a function, and f is a function of the curve such that the zeros of the inverse of the function, okay, I know that this is a little bit weird, but if you don't know the, I mean, if you don't know the algebraic geometry that is behind, I have to use this terminology, are at most the points that I took in the second place. So basically what I'm doing, first, I take a set of functions of my curve, okay? And those functions, all of them, they have the property that when you look at the zeros of the inverse, at most you have zeros in the points that you fix here. And now that I have all those functions, I evaluate those functions in the points of the curve that I have here, okay? So these produce a set, okay? This produces a set in FQ to the n, okay? So now, of course, you have a result that tells you that this is a linear code, okay? That this is defining a vector space. And why is this defining a vector space? Actually, because the set of functions that I take in here, if I have two functions here satisfying this condition about the zeros, then the sum of these two functions satisfies again the condition about the zeros. So I have it again, right? So I mean, I have this is a subvector space of FQ to the n, okay? So this is the definition, okay? Here I just defined a code. So which ones are the ingredients here for the code? Basically, I need the curve, the equation of the curve, okay? And I need the two sets of points of the curve. This is what I need, okay? So those are the ingredients for defining the code. Now, some properties of this code. Theorem. This, I mean, the proof is not really difficult. The point is that you need to know a little bit about algebraic geometry, and I'm not sure you know this. So this is why I'm not going to do the proof, but you have the proof in the notes. So if you know about this algebraic geometry, the proof is really 3 lines, okay? So it's not difficult. So theorem, CDG, is a linear code of length n, dimension k equal to n minus g plus 1. So m is the number of points I'm getting here, and g, this is a nice part, so the geometry is coming. G is the genus of the curve. So what is the genus of the curve? So if your curve, for instance, instead of being defined over FQ, is defined over the complex numbers, a curve is just a Riemann surface. And then you know that Riemann surface, well, one way of classifying there is by the number of holes. So you can get a sphere that doesn't have any hole, and the genus is 0. You can have an elliptic curve that is like a donut, and then the genus is equal to 1. And then you can have like surfaces with more holes, and the genus is just the number of holes that you have, okay? So I mean, basically, this genus, you can read it from the equation of the curve. So it's just a property that depends on the curve, okay? So what is important is that you control the length, you control the dimension, and now we have a bound for the distance. And the minimum distance is greater or equal than n minus m. That is equal, if you want, if we use this equality here, we can write it as n plus g minus k minus 1. So I have an equality for the distance. So now, of course, I'm going to be interested in finding good curves with a good set of points in such a way that I'm going to define a code that the minimum distance is big. Right? This is going to be the goal in order to get like a good code. So how can I do that? So I'm going to, the equality that I wrote here, let me rewrite it in another way. Okay? I can write it as d plus k greater or equal than n plus 1 minus g. Okay? I'm going to divide by n in this equation, both sides. Okay? So I get d divided by n plus k divided by n greater or equal than 1 plus 1. Let me write it like minus g minus 1 divided by n. Okay? But which ones are these numbers? This is the information rate, right? Do you remember? We saw that in the first lecture. Information rate. And this number, we want this number to be big, because that means that we are not sending that much redundancy, okay? But on the other hand, this number is the relative minimum distance. So we also want this number to be big, right? Because this is going to allow us to correct many errors. So basically the idea is that when we are constructing a code like this with a curve and a set of points, what we want is this thing to be big, that is equal to 1 minus this thing. So basically we want this thing to be small, right? We want this to be small, okay? But what is this? G is the genus of the curve. So if we want this to be small, we want the genus of the curve to be small, let's say, okay? But on the other hand, we want n to be big, because n is in the denominator. But n is the number of different points I have to get here. So basically, what do we want? We want a curve with a small genus and with many points, right? So we want curves with, let's say, many points for a given genus. Okay? Yes? Yes. And then g is greater than or equal to n minus m. Is it n plus g minus k minus 1 or n minus g minus k plus 1? Okay, maybe I made a mistake. So here I have to do minus k plus g minus 1. So, so this is a plus. Yeah, thank you. Yeah, definitely. And then here I did it right. Yeah, definitely. Thank you very much. I like this because this means you are following what I'm saying. So I'm going to do it on purpose. I'm going to do like a small mistake just to see if you correct me or not. Okay, so I was saying the idea is that we need curves with many points for a given genus. Okay? So now I'm just going to state a theorem because it's a very famous one and I think that you should know it. So it's a theorem that gives us like a bound for the number of points for a curve defined over a finite field of a given genus. Okay? So this theorem is called the Haas-Weil-Serre bound and says that if X is a curve of genus G, Well, I mean, again, I need the curve with the properties that I wrote here, like absolutely reducible and non-singular, okay? Well, and projective and like so many good things. So if I have a good curve, let's say, of genus G over FQ and if NQ of X is the number of FQ rational points. So if I need to take n points in the curve, I'm going to need n to be smaller than this, because this is going to be the total number of points that I have, okay? On X, then the following bound holds. This number of points minus Q minus 1 is smaller or equal than G times the integer part of this number. Okay, so this is a very famous inequality that basically is telling you, I mean, this is the absolute value. So, I mean, if we are looking, so basically this tells you that Q plus 1 minus G times this is smaller or equal than NQ of X, that is smaller or equal than Q plus 1 minus G, divided by this. Okay. Okay, so basically this tells you, sorry, this is a plus. This tells you that if you are fixing the genus and you are fixing Q, then the number of points is fixed, is bounded by this number. So here the n cannot be that big, I mean, is bounded by G, okay? But anyway, what we saw is that it is interesting to find curves with many points, because those ones are going to give us like good codes. And this is why now I'm going to, I mean, you have the link in the notes in the web, but well, anyway, the web page is easy. There is a web page that is called Many Points .org, and in this website you're going to find like so many tables. Do you remember that last week I told you about those pages in which you have tables with codes? That you fix the dimension, the length, and then it tells you, oh, so the maximum minimum distance that you can get is this one, and you can construct the code in this way. So, I mean, in this way you can look for codes with good properties, right? So now this is another website in which you can find like so many tables, and in this time what you get are curves. So this time the parameters are the genus and the finite field, the Q. So given a finite field, so this is given a Q and given a genus, now in the tables you can read the curves with the maximum number of points that you can get. Okay? You know that this number of points, of course, is going to satisfy the Hasse-Weil inequality, that is this one. And again, you can find in this table like so many open problems. That's it, there are some cases in which we are not sure about which one is this maximum number of points. And still there are like open cases that they don't look to be that big. So you say, wow, it's funny that people didn't find like those examples, those curves. But I mean, actually it's difficult to construct these kind of curves. So for instance, now, I mean, I didn't write it, but I mean, you can check in the website. The first open cases, if you want, they are for Q equal to 2 to the 5 and a curve of genus 4. So this we don't know. And for instance, we neither know for Q equal to 3 to the 2, and also I think that is genus 4. Well, you can look it in the table. So for those cases, we are not sure. Like, you know, we have like some bounds. We know that the maximum number of points is going to be this one or this one. But I mean, we don't have a curve with this one, so we can say it's this one. Or we don't have a theoretical result that says, oh, it cannot be this one, so it has to be the other one. So here you have more open problems. I mean, if you want to try to find those curves, you can have fun. And then, of course, you can email the people maintaining this website and saying, hey, I found the curve you were looking for. And then they write your name. They write, this person found the curve that we're missing, and now we completed the table. So, I mean, I invite you to visit this page and take a look. Okay? So, yeah, what else? And the funny thing, because I mean, I said that this is important in order to construct good codes. So now I'm just going to state like a result, well, a definition of what is a good code for this, and a theorem that says that actually there exists good codes constructed in this way. So I mean, it's worth it to try to find these things. Of course, this theorem is not I mean, you don't get explicit construction. It's just a system theorem that tells you, oh, there exists good codes that you can construct like this. But the theorem doesn't tell you how to construct them. So, well, you have to look for them. Okay, so I'm going to start by giving the definition. So, definition, a sequence of curves xm over fq is called asymptotically good if the limit of the number of points when m goes to infinity of this curve, of this sequence of curves, is equal to infinity. Then we also need the genus of these curves to go to infinity, right? Because if the number of points, I have many points, goes to infinity, also the genus, because the genus is giving to you a bound for the number of points. So, I mean, we also need this thing to go to infinity. And what we want is that in proportion, this number of points is bigger than the genus, let's say. And such that the limit, when m goes to infinity, of the number of points divided by the genus exists and is still positive. Okay? So if you find a sequence of curves with this property, you get what is called an asymptotically good sequence of curves. Okay? This thing to be positive is basically, I mean, for having this control. Okay? It's this quotient. And there is a very famous theorem. This I'm not giving the proof, but I'm giving some ideas due to Sussman, Bladut, and Sink, that basically I'm not writing this with all the details, but if Q is a square, then there exists asymptotically good sequences of curves. So you have good codes, okay? So this is an existence theorem. And I mean, what is funny, the only thing that, and I want to stop about the algebraic geometry GOPA codes, the idea for doing this is that the construction, he constructs like the sequence of curves by using modular curves. So modular curves are quite related to modular form that you have been studied also those weeks, okay? So I mean, at the end you see everything is related with everything. So, okay, so this is what I wanted to say about those algebraic geometry GOPA codes. Indeed, you can construct like very good codes using curves. And now we are going to see the applications of this thing. So I'm going to focus now on the cryptography. So let me erase here. So about the cryptography, I already said it the first day. What we want in cryptography are problems, mathematical problems, that one direction is easy, and because it's the direction that we are going to do, and then the inverse direction is difficult, because this is the direction that someone that wants to attack our privacy is going to use. So example of that, and I think that Michel is going to talk about it during his last talk, is the discrete logarithm problem. You know, this is an example of problem that is easy, so I'm going to write this. So if I tell you to compute a to the n, this is easy, you know how to do it, right? But now if I tell you that there is a number b that is equal to a to some power, and I ask you to compute this power, this is difficult. Okay? So this is an example of problem that is very used in cryptography. And this is called the discrete logarithm problem. So I'm not talking about this one, but it was just for giving to you an example of the kind of problems we are looking for. It's a problem, so, well, you agree that, I mean, computing here the exponentiation and here the logarithm, they are inverse problems, right? Okay, so this is the type of problems that they are good for cryptography. So another well-known problem that you know that is used in cryptography for the, I mean, I don't know how much cryptography do you know, but I'm sure that you have heard about these things. So well, so this is what is called for the logarithm, sorry, discrete logarithm problem, because in French it's the other way around, so. The discrete logarithm problem, so you have this one. Then, I mean, there are other crypto systems that they are based on the difficulty for factoring integers. So, I mean, this is like the RSA, okay? So, I mean, this is based on the difficulty of factoring. So, integers. So again, if you want here, the easy problem is making a multiplication. So I mean, this is easy, we know how to do it. But now the difficult problem is if I give you the integer, give me the factorization of this integer. Okay? So this is another example of problem that is good for crypto. And well, what happened? I mean, I guess that you heard recently that so many people, they are talking now about quantum computers. Have you heard about that? This is something that is very, very cool and everybody talks about it. Have you or not? Yeah? So I mean, these super quantum computers that, I mean, even Google is working a lot on this and they are working super hard on constructing those computers. So the funny thing about these computers is that they are able to solve difficult problems. So for instance, well, these two problems. So with a normal computer, they have those problems are difficult. But with a quantum computer, those things are easy. So basically, if you have a quantum computer, you can break like all the crypto systems that we use nowadays. So I mean, this is very dangerous. The point is that constructing a quantum computer is actually not that easy. Okay? Because you know, a quantum computer, the thing is that it's made of qubits, so it's like with quantum physics, and well, it's a complicated thing. But the idea is that with a quantum computer, there are things that can be solved easier than with a classical computer. Okay? An example of this is like, imagine that you have a list, a set. You have a set of n elements, as we had before. And you want to check if there is a fixed element that is inside your set. Okay? So this, I mean, with a normal computer, whatever you do, what you just have to do is the element that you want, you have to compare it with all the other elements in the set. So, I mean, you are going to do as many operations as elements you have in your set, okay? But with a quantum computer, instead of having, for this problem, complexity, the order of n, let's say the length of the set, you have complexity a square root of n. So, I mean, then this problem is much easier to solve with a quantum computer. Okay, this is because of the quantum physics, and I mean, instead of having bits, you have something that is like a combination of bits. So, well, you are allowed to do these kind of things. So, well, I mean, don't worry. Google announced that they constructed something close to a quantum computer. So we were, oh, but then they can factor integers. Yeah, but they can factor integers. I mean, if I'm not wrong, the last thing that I heard is that they are able to factor 21, but they have to know that it has 2 prime factors. So, you know, I mean, for this, I think we can all do it this, you know, by head. You don't need a quantum computer. But, well, they hope that one day they will be able to have one of these super cool quantum computers. So, I mean, the RSA and all these crypto systems will be broken. So, well, the thing is that, yeah, right now we don't have those computers, but maybe in the future we do. So we need to look for new hard problems, you know, that they are quantum resistant, we say. That even if you have a quantum computer, then you cannot break them easily. And, well, there are different crypto systems, options that you can use. So, I mean, I'm going to just write the name of the different options that we have nowadays. So, one is basis of Euclidean lattices. So, I mean, I don't know if you heard about this. It's like if you have a lattice, I mean, you saw lattices this week, so you know what is a lattice. So, I mean, a lattice have like many representations. So I give you a lattice, whatever the representation. One of the difficult problems that is hidden behind this is to find what is called the shortest vector in the lattice, okay? So this is one thing. Then we have, so I'm going to leave for the end the ones with codes, okay? Then we have one that is with elliptic curves. Isogenies, okay? Those are very nice. I work on things closer to this thing. Then there is another one that is polynomial system equations, okay? That basically is I give you a system with so many polynomial equations and I ask you to solve it. This is difficult. I mean, a linear system of equations, we perfectly know how to do it with Gauss elimination, but a polynomial system of equations is like, wow, now I don't know what to do. And then there are two other options for these post-quantum crypto systems that people are working on to get some alternative to the old or classical crypto systems that we have. And one is based on the rank matrix code, and the other one is based on Hamming, sorry, I wrote matrix, but it's metric code. So among the 5 alternatives that we have for doing a post-quantum crypto system, or quantum-resistant crypto system, there are 2 of them that they are based on code. And this one, the last one, are actually based on the kind of codes that we were looking at this last week. Okay? Because this Hamming means that we consider the Hamming distance for the codes, and this rank metric codes is because you are using like a different distance. But let's say that those ones here are the ones that we haven't studied, okay? So now, you know, there is this international competition that is called NIST. Well, I mean, this is depending on the state. So, I mean, there is this competition where people submit like crypto systems that they claim that they are quantum resistant. So there are some people like trying to evaluate which ones are the best ones, which ones are the worst ones. And, well, I mean, several crypto systems pass through the different rounds of these competitions. And I mean, many of them, they were actually based on these Hamming metric codes. So I mean, what I mean is like, yeah, they are really, really crypto applications for this thing. It's not that, you know, sometimes when we do research, we say, yeah, and these can have crypto applications. And we just say it because then it's easier to ask for money and for funding for doing your research. But no, I mean, this time when I'm saying that they are crypto applications, I mean, it's totally true. Like, if people are working nowadays on getting like good crypto systems based on those codes. So, I mean, I just want to say a few words about the advantages and disadvantages of these crypto systems based on code. So, the thing is that I have some numbers here. Well, maybe the numbers are not important. But if you want like the advantages of those codes are that the ciphering and the ciphering is very, very fast. What is the ciphering and deciphering? Basically is the coding, the encoding and decoding. But because there are some crypto behind, we call it ciphering and deciphering. But it's the same thing that we saw, okay? It's encoding and decoding. So, I mean, this is like very, very, very fast if you compare with all the other methods. So this is one of the advantages. And of course, the other advantage is that it's post-quantum resistant. So as I said, the discrete logarithm problem and the RCA is not quantum resistant. And if you want the problem, I mean, this is the reason why this is not the clear winner between among the 5 crypto systems that we have here, is that actually what is called the side of the key, disadvantage, side of the key is very big. And what is the side of the side of the key? So basically, the side of the key is when you do the ingredients for doing your crypto system. So here, the side of the key is your code. So basically, it's a description of your code. And I mean, describing a code, even if you give the generator matrix, this is going to be huge. So this is a lot of information that you have to give. Because even for these algebraic geometry codes, you need to give the curve, you need to give the points, but then you need to compute a basis for the functions that they are in the definition. And I mean, this is going to be a huge matrix. So basically, this is, let's say, like the huge price to pay for using this method. So I mean, this is also something that people are working nowadays, that is to try to get like how can you represent the code in a better way for not having such a big side, okay? So now I have 10 minutes. So in these 10 minutes, I'm going to describe the crypto system, because I'm saying, yeah, you can apply the codes for doing the crypto system. Okay, but how does the crypto system works, right? So I'm going to give you the details. Okay, so what is the idea? So, well, what are you going to need? So I'm going to, so what you need for your, well, this is called the Macaulay's crypto system. Okay, so what you need for your crypto system is first, F, a set of code of dimension k in FQ to the n. So it's not only one code that you need, but you really need a set of code, okay? Then you also need S, a set of secrets. So I mean, those secrets are the things that you want to send, okay, to someone else in a secret way. With a map that goes from the secrets to the codes, okay? So if you want your secret, I mean, it doesn't need to be like a secret. It just may be like an email that you send to a friend. That is secret, because when you send the email to a friend, only your friend is going to be able to read the email, okay? So the secret, you can think that is an email. You want to send an email, okay? But then you have a map that for each email that you want to send, or there is a map that starting from your email, you get a code, okay? And now the other thing that we need is that to each secret, you have an algorithm associated to S that corrects the errors for the code associated to your secret. So basically, this is a decoding, okay? So yeah, I mean, you see, this is what I was saying, that the key is very big. So basically, you need like, well, a lot of codes, then from each secret, a maps that give you a code, and then for each different code, you have a decoding algorithm that allows you to correct the secrets, the errors, okay? Okay, so now that you have this, let's see which one is the scheme. How does it work? Okay. So Alice, this is always, you know, Alice and Bob. Alice wants to send an email to Bob. Alice and Bob and the generic names that we use. So the secret key of Alice is one of the secrets that we have here. Okay? And with generator matrix G. So the first thing that Alice do to create like some redundancy and to complicate things, well, at the end, this is Gmail or Hotmail who does it for you. But I mean, I'll explain later like the comparison of the scheme with the fact when you want to send an email, okay? So Alice take a random invertible matrix S and a permutation matrix P. So basically here what Alice is going to do with the generator matrix, first is that you modify it with an invertible matrix. So this is like taking a different basis for the same code. And then a permutation matrix that is going to switch the columns. So, I mean, it's like you hide everything. So the private key, so only Alice know this, are going to be S, G, and P. Okay? So this, if you want the private key, is your password. Okay? And now, the public key is going to be, she is going to make this thing public. So this product of matrices. So if you want, this is her email address. So your email address is public. It's the way in which people can contact you. Okay? So this is the email address, and this is your password. So now, the encryption. So Bob wants to send the message M to Alice. Okay? So Bob is going to compute C equal to M G prime. So this is like sending the message using the email address of Alice. Okay? And what he does is like he takes this, but he doesn't send this directly. Okay? Now what he does is that he produces Y equal to C, this thing, because he's going to make things difficult if someone wants to understand the message. You know, I mean, because here it would be easy. You just have to multiply by the inverse. This is public, right? So to make things difficult, he's going to add some error. So he's going to add to C a vector E of weight. So weight of E is equal to T. Okay? So now Alice receives Y. So what happens if someone else takes Y? Okay, you take Y, but there are errors. So, I mean, how do you recover the original code, the original word? You have to decode. You have to correct the errors. But this is difficult. This is a difficult problem. Okay? So, I mean, the security of the crypto system is here. But now the thing is that Alice received Y. So what does he do? So the decryption is that first he computes C prime equal to this thing, Cp minus 1. Okay, so remember, P, it was permuting the columns. So now when you do that, you put again the columns in the right position. But this is something that Alice can do because Alice knows the private key. So P is here, okay? And now apply the decoding algorithm that you get from here. So in order to find M prime, okay? And now finally, she computes n equal to n prime s minus 1. This is just a chain of bases, okay? Because remember that with multiplying by s is like we consider another base of the code. So this is the algorithm. And basically, I mean, the metaphor, I mean, the crypto system like this maybe looks a little bit weird. You don't know what is the private key, what is the key, the public key. But at the end, it's just that. Private key is your password. Public key is your email address. M is the email that Bob wants to send to you. And then all the operations that they are in the middle, let's say that is Gmail or Hotmail or whatever the kind of email that you use, who does the work for you. You just have to introduce your password, and then your server, your mail server, can do the computations that appear here. And I mean, this is used nowadays. The problem is that the key is very big. So, well, sometimes when you have a crypto system, what you do is like you use like different crypto systems. You use something for, I don't know, encrypting the password, and then you use another crypto system for encrypting the message, and then you use another one, so you get a combination of things. So if you want to encrypt something that is not very big, like for instance a password, this system is very good, okay? So, okay, it's just 10:20. I cannot do the example. I prefer you to keep with this. So, I'm done. I hope you enjoy the course. Questions? Yes?
I still don't understand the part, the decryption part. Alex receives Y, then how could we know the C?
Oh, because, I mean, in order to get here the C, you need to correct. You know, it's like the problem, like when you have your code, you do the balls, and if you get something that is here, you have to get like the closer vector, that this is the difficult problem. So this in general is super difficult. So in general, nobody can do that, but Alice can do it. Why? Because Alice knows this. You have a decoding algorithm. And for these algebraic geometry codes, there exists very good decoding algorithms. But this is something that you keep secret. So I mean, this is part of your password, let's say. More questions?
So Alice applied the algorithm first, or C found the C type first?
Yes.
C applied the algorithm first.
Yes.
Then find the C.
You're welcome. More questions? Nobody asked. Here the typical question always is like, but do you really believe that a quantum computer is happening soon? Always the question. So I'm going to reply, actually, I don't think so, but we'll see. Maybe I'm wrong. Okay, thank you very much. Bye.